Yeah, it's making all the chat big. I mean, it's fine. It's better that it does that than not work. Yeah. Although I do need to mess with the font color still. My background does not go well with that. Yeah, I think so. Mm. Yeah. Yeah, I mean, like I said, it works, which is better than it not working, so. Oh, you've been tossed into the beam dump. Yeah. Yeah. Also, coincidentally, I do have green tea. Yeah, we can. If it, hello. It was fun, and I can bet. I just I'm relegated to blackjack. That was the only game I was on average winning at. Yeah. Um, well, so I have been to like the Kentucky Derby has a museum attached to it. So I've been there. And it's a very interesting and I've been learning a little bit about the horse racing lore in Japan, which is also a bit interesting. Tyler asks if, yeah.
Oh, I am. This whole time. Rip. Whatever. Yeah. Introducing us all up again. I guess I just haven't used this particular channel.
Yeah.
This scene in a second. So.
I have not used Just Chatting in a while, but yeah. So we interrupted ourselves, but yeah, today we are gonna be talking about the wonderful thing that Mr. Fourier invented, otherwise known as the Fourier series and transforms.
That's right. What's the deal with the Fourier series? I missed that show. Did season 3 get good?
It kind of drops off, but then it comes back up, but then it drops back off again, and I don't know how to describe that behavior. It just keeps going back and forth.
Ah, very interesting. Then let's go ahead. Tell us first about what the deal is with this Fourier dude. What's the deal? Why do we like this guy? Why is it French?
Yeah. So well, yeah. So Joseph Fourier was a French mathematician and scientist in France in the late 1700s and early 1800s. He made great contributions in the field of thermodynamics, and his, I guess, overall Fourier series and transforms are very useful in just anything that has harmonic behavior can, even if it's very complicated, Fourier gave us a way to kind of break it down into digestible components is I guess how I would describe that.
Is that right? I dig this. I'm looking them up right now on the wikipedia.com. Very legitimate source.
Yes. Yes. Well, yeah, so I want to bring up the anecdote I found while perusing that Wikipedia page. So on the Wikipedia page, let me pull it up on my stream. So on his Wikipedia page, there's a section that mentions in his works. Random internet shit. There we go. Alright. I don't know if you can read that, chat, but okay. But there is a part okay. When he did his treatment of like heat and thermodynamics, it mentions that Fourier may have beaten Bessel to the Bessel functions.
This isn't the right one.
And so I've highlighted that sentence. And so this isn't about Bessel, but just to give a brief description, Bessel functions are kind of like sine and cosine, except sine and cosine are good functions to use to describe situations where you have rectangular symmetry, like a box or a prism. Bessel functions pop out whenever you're dealing with cylindrical symmetry. But yeah, so I was, skeptical, as one should be in science, and I managed to find a translated version of this paper that Fourier did, and in the he does this like cylindrical heat equation, and wouldn't you know it, he gets J0, the zeroth order Bessel function, as the radial solution.
That's interesting. So zero order, and I remember seeing this from like math methods as well. It's all of these different kinds of functions, like Rodriguez formula, Frobenius method, all these big boy terms. I do remember us probably solving for J0. Actually, I distinctly remember that now. But probably for classical mechanics, actually.
That's interesting. I haven't had to use it in classical. It pops up a lot in like E&M and quantum, from my experience.
Interesting.
But yeah, Bessel functions are my favorite functions. For genuinely no real reason, but they are.
just because they're cool. Yeah.
Yes, they're cool.
They're different.
They
terms.
look cool. Their behavior is cool.
Yeah.
But maybe that should be saved for a future stream.
Yeah, we can always break down like the math end of it and just be like, because I'm looking at the formula here. It's J alpha equals the sum, infinite sum from m factorial gamma. All these terms. So what's very interesting, and then there's the integrals too that are also pretty interesting.
Yes.
Now, how does this help us with the Fourier? What is the deal with the Fourier series? What is the deal with all this Fourier stuff? I am very interested in this. I have never heard of this ever in my life. I need to be sold it. Tell me what this is, man.
So I work more at the Fourier Transform, so I'm going to sell that. So imagine you're trying to receive some radio signal or some sound signal, and you want to analyze it on your computer. Well, in the time domain, it's going to look very messy, right? Because you have your actual signal, it's going to get mixed in with, you know, background noise or some dude screaming 2 doors over, that kind of stuff. You need a way to separate out the noise from what you actually care about very nicely. And the way you can do that is the noise is going to come at a different frequency usually, or a different set of frequencies than what you are looking at or what you care about. And so the Fourier transform, which in essence transforms a function from one domain into its Fourier conjugate domain. And an example of this being, if you have a function f of t, where t is time, its Fourier conjugate is frequency, because it's 1 over time if you're looking at the units. So you can take this time domain sound signal and transform it into the frequency domain, and it'll give you a distribution. Instead of looking at the way the sound changes over time, it gives you the spread of frequencies and how much each frequency contributes to the overall signal. And in that, once you have that, then you can much more easily go like, all right, this is noise, this isn't what I care about, let me get rid of that.
So you're telling me that there is a way to get signals, data, and you can separate out a bunch of the values in waves, sines and cosines. Is that right?
And this is part of my presentation later, but at least in physics, a lot of physics is much more easily done in the frequency domain. So for instance, in my research, which is optics, whenever you're talking about a material's properties, say for instance its index of refraction, it's much easier to talk about how the index of refraction changes based off the frequency of light that's hitting it, versus rather than just saying how the index of refraction changes over time. Physically speaking, that doesn't make as much sense, at least from a physicist's point of view.
Oh, I see. With light too. That's
also,
yeah. Also what?
No. It's I'll bring it up later, but it's also so it's also useful because monochromaticity, right? Mono meaning one, chroma meaning color, right? So in this case, whenever I'm talking about monochromatic, I mean one color, one frequency. In reality, that is impossible. That is almost impossible. So that means you're always going to have some kind of frequency mixing in your light source. So you do need the Fourier transform. You can't just take one frequency.
Wait, surely you can do that though with polarizing some stuff. Maybe you can get like a certain wavelength through like a filter, right? Like a polarizer or like a lens. No?
So a polarizer will separate out the spin, or the polarization of light, but in terms of frequency, like color filters, usually because of different material properties, you'll never get a single frequency color filter. You'll always see some viable range, right? Like say 800 nanometers to 1200 is what works best, or what passes through it the most. And the same thing is true of lasers too. Even though lasers are in theory monochromatic, they are not in practice monochromatic. You will always have some bandwidth.
So it's good to break that stuff down and Oh, there's an inverse form too. Huh. So,
yes. So Fourier transform. So any linear. Yeah.
Let me ask you this. I've often heard this referred to as the thing what makes cell phones work, or any sort of like wireless technology, right? Is that not the case?
That is the case, and in fact, I coincidentally went down a rabbit hole last night. So again, cell phones and Wi-Fi rely on electromagnetic signals, usually in the radio frequency range. So the way, or at the most basic form, because I do not work with the radio frequency range, the way cell phones and Wi-Fi carries data is it typically has what's called a carrier frequency. So it picks one frequency or one small area of frequencies that carries the data from one point to another, and then it uses different it either uses different frequencies or different kinds of methods to encode on top of that the actual data that it's trying to convey.
Interesting.
So the actual algorithms used are very complicated to make it efficient, and I do not understand all of the ways that Wi-Fi and cell phones work, but that is in essence how it works. You have a carrier wave and a signal on top of that, superimposed on top of it, and so the Fourier transform allows you to separate out the carrier wave to actually get what you want out of that signal.
That's very good then, because obviously we're all spouted out with like all the different kinds of radio waves, frequencies, and everything. Like it's actually very, very noisy.
Yes.
I bet.
Yeah. So radio sources are everywhere. We have AM, FM, all sorts of cell phone datas and cell phone data sources. So it helps to have radio. I know in America, at least, we have, I believe it's called the FCC.
Yeah.
That controls which frequencies of radio waves correspond to which channel. So actually, if you're ever in your car and you say you want to listen to 109 FM, right? That's the carrier wave frequency that you're tuning into, that your radio is tuning into. So in this case, it's it would be 109 megahertz, I believe. And so that's the carrier frequency that your car's radio will tune into to pick up that specific radio station.
I see.
That's also why. So radio stations are local, right? Because they don't have a lot of power.
Yeah.
So if you're ever crossing into an area that has two stations at the same frequency, that's why they'll start interfering with each other. The two signals are mixing because they have the same carrier frequency.
Oh, so like when you're driving away from a town or city, and the next radio.
Yeah.
I see. And I pulled up the Wikipedia articles. I put them in the chat. So the difference, of course, between this is just one style of broadcasting, right? FM and AM. I'm familiar with that. One of them is really good for just getting sound through, and the other one is really good for quality music and stuff like that, right? So it is every single signal between these two, is it all FM and AM, or do other wireless technologies have their own style of it? Do you know? Because I'm curious about that. Are they all?
Yes. Internet uses, Wi-Fi in particular uses I forgot the name of it.
IEEE 802.
ODFM. Hang on. It's specific, but the algorithm they use is orthogonal frequency division multiplexing. So that's obviously very different from standard AM/FM. And again, I read over this last night because I got curious, but I don't understand all of it. But it uses a method of modulating both the frequency and the phase of your waves. So for those that might not be aware, whenever you're talking about like a sine or cosine wave, you can talk about it. So any kind of wave like that will have an amplitude, a frequency, and a phase. So a constant shift left or right from the y-axis, right? So modulating any of those three or a combination of those three are used can be used to carry data. All you need is for binary, at least, all you need is a like, oh, if I shift it this amount, it's a 0. If I shift it this other amount, it's a 1.
I see. So that's why, like, other than like different kinds of delivery methods, like optics and stuff like that, that's how you're able to tell between the sound. You can identify a 0 or a 1 based on several different things from a wave, which could be the frequency, the amplitude, and all that. That's pretty interesting, right? So that's why we like have giant, huge like antennas, like looking up at space all the time to listen to it, right? Because anything out there could be interpreted.
Yeah, so like even Z, who's the cosmic microwave background. Microwave is also a range of electromagnetic waves, which has its own frequency range. And so we would need Fourier transforms to isolate that signal from other sources.
That's pretty cool.
I mean, so I'm not as well versed in space stuff, so I don't know the specifics about how they do it. But yeah,
I can talk about that just for a sec. I think I get the gist of it. So basically, any sort of particle, any sort of like element, right? We know either produces light or it has its excited state, right? So like the electromagnetic bands, I believe that's what they're called. Or it's when an electron goes from an excited state to a grounder state, and that's when it releases a photon, right? So that stuff is one of many things that you can detect for space, so you can identify what elements are actually in a nebula, or what sort of weird, just different things are out there. And of course, depending on how intense the wave is and all that, it'd be really convenient to identify.
Yeah.
So pretty cool. Let me see. Do you have a favorite? Do you have a favorite kind of wave? Let me ask you that. Or in method.
Of wave?
Yeah. So like maybe like method, yeah. Or even like electromagnetic spectrum. Like I think gamma waves, gamma particles are pretty cool. Yeah, gamma rays.
So okay, I'm gonna be biased because I work in this area, but anything in the terahertz frequency range is interesting.
Terahertz.
So terahertz is in between microwave and far infrared. So it's sometimes referred to as the terahertz gap, because the wavelength of microwaves are big enough that you can use electronics and stuff to make detectors for it. And IR is small enough that IR is small enough that there's another type of method that we an optical methods that we can use to detect it. But that gap in between, like I believe 0.5 terahertz and 30 terahertz, up until relatively recently, was very difficult to generate and detect.
Oh really? It's so strange.
Yep.
So yeah, I'm looking up the article right now. It says between 100 microns and 1 millimeter. So between that range, is that right?
Yeah, that sounds about right. 1 terahertz will be about 300 micrometers. So.
And this is a new space that is now getting like some attention. Huh. Oh.
Yes, and by new space I mean like 70s, 80s.
Oh. Okay. Naturally, this also occurs at parts of black body radiation for temperatures greater than 2 Kelvin. So that's pretty cold. So, yeah. Anything.
So normally black bodies will tend to peak in, at least for like human scale stuff, will tend to peak in like mid to near IR. So like thermal cameras and night vision is based off of mid to near IR detectors.
That's really cool.
Because that's the peak wavelength range that we give up, because we have a temperature, right? So humans give off black body radiation.
Just because we're hot.
Yep.
Anything with energy then.
Hot in here.
Just take off all your clothes.
Yeah.
Huh. And that's actually really cool, because I think that's all just because of how like energy works, right? Everything has to produce.
Yeah. I did a stream on this a few weeks ago, but black body radiation almost broke physics.
Oh, really? Why?
Yeah. So if you try and calculate the emission of a black body using purely classical methods, you get a Fourier series. Actually, this is topical. You get a Fourier series. But that means that you end up adding up infinite frequencies, and your energy becomes proportional to the amplitude of your higher frequency components. So that means that as you get into like the ultraviolet range and beyond, your energy emitted by this black body is going to diverge to infinity. But obviously we don't emit infinite energy, right? We'd explode, or we become supernova.
What?
Right?
That'd be cool.
So that that inconsistency in the math and the physics is what we dubbed the ultraviolet catastrophe, and was only solved by Dr. Max Planck by introducing the fact that energy is quantized, which means that as you increase in frequency, the actual probability that you'll emit in that energy range becomes smaller and smaller.
That's very interesting.
So it becomes finite.
Okay. It's also referred to as the Rayleigh-Jeans catastrophe. Rayleigh did a lot of like space, atmospheric wave stuff, didn't he?
Yes. Yeah, we have Rayleigh scattering, which is why the sky is blue.
So he's the reason that sky is blue.
Well, he figured out why the sky is blue.
Nope, they changed it after the fact. It was like Newton discovered gravity, it became blue after him.
Yes.
Yeah. So,
yes,
okay.
We didn't have gravity until Newton.
Yeah, I know, spoiled everything. Honestly, think about that. All physics is like that. You discover something exists and all of a sudden you see it everywhere. Yeah, sure, bud. You made it up. But yeah, it says here, applying the new energy to the partition function is in statistical mechanics. Planck's assumptions led to the correct form of the spectral distribution functions, which demonstrates that stuff. That's pretty interesting. And now, is there a history book that you read this from? I'm curious about that, because it will go back to Fourier stuff, but I'm curious as to like how you end up discovering this.
It wasn't a hit. So, and this is why. So, during the course of my physics degree, you start with General Physics 1, which is classical mechanics, and waves. General Physics 2, which is basic E&M and optics. And then after that, you take either General Physics 3, it's sometimes called, or Modern Physics, which is what it was called at my university. And so the way my professor taught it, so modern physics refers to any physics discovered during the 20th century. So this UV catastrophe was at the turn of the 20th century. You have special relativity right after, quantum. And so my teacher kind of taught it chronologically. And she actually talked about the motivation behind why we had to fix these issues. Why did we need special relativity, right?
Yeah. Okay. So you got like
and so the
you go on, sorry.
Yeah, so it's kind of like a history class and physics class rolled into one. But also the textbook we used talks about the historical context. It's Modern Physics by Ohanian, I believe, and I think I got it for like $7 on Amazon. It is the cheapest textbook I've ever bought.
That's really cool.
Aside, yeah.
I'm looking at Fourier's background as well. He drew pictures for their caricatures. Oh yeah, true. Napoleon appointed Fourier prefect, governor, Warsaw. He appointed Fourier as governor. What? Really?
Oh, yeah, I know he worked with Napoleon, at least. I saw that in the Wikipedia page. Why isn't this showing?
His portrait's pretty interesting. Look at that. He looks fat. Nice. Question for you. I really dig like how a bunch of these people just end up doing stuff and just doing anything, right? They do have the time and usually they have a sponsor and stuff. But I'm like, you know, how do they just go about just doing the things like this? Were they a grad student?
Yeah, so science looks, or the scientific method looks a lot different than it used to. So back in the day, you could kind of dip your toes into a bunch of different topics. So like Charles Boyle did chemistry, physics. I think Volta did both physics and chemistry, because not only do those fields overlap a lot, but we just didn't know enough about any of them. So, for lack of a better term, there was a lot of low-hanging fruit. But nowadays, because, and this is what I think is interesting about the difference between different science courses, is that physics, from what I've seen, physics is a lot more sequential than other science degrees, because it is progressive and we just build and refine our models. The physics degree has gotten longer over time because we've had to add more to our curriculum. Obviously, back in Newton's day, we didn't have to worry about E&M or quantum or thermo. But now it takes 6 years just to get done with classes.
Yeah, that's part of the reason why I didn't pursue a full physics degree. Well, that and my physics department was getting really annoyed at me. So that's another story. But again, I'm not a very controversial person, but like, who cares? But I noticed that there's a lot of like applied things and just so much variety that you have to learn as a general physicist. So, I mean, yeah, I kept up with it just fine. It was a bunch of math.
Yeah, well, it looks like a lot, but if you actually read the course descriptions, what you'll notice is physicists take the same 4 topics, and we take that same topic over and over and over again at increasing levels of math. So, like, my undergrad degree, I took 3 different classical mechanics classes: General Physics 1, Intermediate Classical, and Classical 2. I had to take E&M 3 times.
Oh. Really?
So, yeah.
Like 3 different amounts, right? Not like the same class, you mean, right?
Yeah, not the same specific class, but it was like General Physics 2, Intermediate E&M, and E&M 2.
Yeah.
So when you start a physics degree, because there's a lot of math that you kind of have to know first.
Yep.
Obviously, when you're a freshman or sophomore, you're usually not gonna have already taken those math classes. So they kind of have to simplify the mechanics in E&M a bit. But it still helps to get you a general grasp on the physics, the concepts, right? What is an electric field? Why do balls arc in a parabola when you throw them, right?
Yeah.
So they give you those courses first, and then after you get through your calculus classes, then they're like, all right, you know how to solve a differential equation, you know how to do vector calculus. Now let's go back through these topics and take the training wheels off a bit.
Yeah.
Let's not neglect air resistance.
Right. That's always really hard to do too, because even then, like, I don't think they had the calculus at the some different stages for like differential equations and stuff like that, because I believe that's also like air resistance, for example. Yeah.
Yes.
So
it is very easy. It is very easy to quickly go from a problem that has an analytical solution, meaning you can express it as a function, to I need to throw this into like MATLAB or Python.
Yeah.
Because you can't solve the differential equation. That's why, actually, so a famous meme amongst physics majors is the small angle approximation. So
oh yeah.
Yeah, so a small angle approximation, right? So sine of x. If you take its Taylor series expansion about x equals 0, and you take the first few terms, right? You get x minus x cubed over 3 factorial plus, x to the 5th over 5 factorial.
Yep.
And then minus so on. But for very small values of x, right?
Mm-hmm.
If you take like 0.01 and cube it, that just makes it even smaller, right?
That's right.
So for very small values of x, you can kind of just ignore the x cubed, the x to the 5th, and so on.
Mm-hmm.
And so you can say that sine of x is approximately x.
Just about, yeah.
And this is important. And this is important because if you're trying to figure out how a pendulum moves, just a simple pendulum, or just a rod and maybe a thing at the end, the differential equation becomes a function of sine of theta, the angle between the pendulum and your vertical. You can't solve that differential equation. That is a nonlinear differential equation. You have to assume that theta is small.
Okay, that's fair. I have a video actually of a pendulum that I coded specifically because I did cover that in my classical mechanics class. I'm trying to find it real quick. I'll showcase that. But I remember learning about it, and yeah, small angle approximations are good for about 8 degrees, or about 0.14 radians.
The rule of thumb we typically use is anything smaller than 30 degrees.
Yeah, that's quite generous. Which it still works.
Well, you know...
I know what you're saying. I don't...
Yeah.
Let me turn that
I mean, there's a specific problem within statistical mechanics. If you try and model the, I believe the density of state of a neutron star, you can approximate it as low temperature.
Oh?
Yep. A neutron star. You can approximate it as cold.
Oh. Why is that? Because of the spin? Or
no, because relative to the like nuclear interactions and the other energies you're considering, the black body temperature is much smaller than the other energies, or like, yeah. So you can use whatever formula you had to use. You can take the low temperature approximation.
Oh. Okay. See,
and it aligns fairly well to observations as far as I know.
Being a little too liberal with your numbers here. But you know what? I totally get it, because honestly, after some point, yeah, what's the value of like learning the 10th decimal of like some things? No, you can approximate stuff. I get it.
Yeah, yeah.
And as a practical matter as well, like computation is really expensive. So like back in the day when computation efforts were, you know, you either had to know it or you had people dedicated to solve these things for you. Which there was a job, in fact, to just be a computer. So it was pretty
It was actually,
interesting.
if I remember correctly, mostly female dominated.
Yeah.
I think, yeah, a lot of the early astronomical calculations were done by women.
Interesting. Yeah, huh? Also, I pulled up the video. Yeah, it's
if you
let me send it over.
If you want to screen share it with me, yeah, I can.
Shoot. I'll send you the file. It's a
well, I was just
file.
saying, if you screen share it on the Discord call, I can just throw the Discord call, the screen share.
The shenanigans. Let me see. I'll just share you my OBS, I suppose.
We've also gotten severely off topic, but
yeah. Well, we're gonna come back. We're talking about our experiences.
We'll get back eventually.
Yeah, we're fine.
Yeah.
That just shows you that, you know, we did stuff, didn't we? We totally did stuff.
Yeah.
In our degrees, small angle approximation.
I remember about at least one thing from my undergrad degree.
Yeah.
I remember frighteningly little from my math major.
Oh, that's ironic, because I kind of have the opposite. I learned a lot from physics, but I also did not. There's so many details that I cannot remember for the physics.
I mean, in all fairness, there's a lot of physics details I don't remember. I was talking with a friend who's an underclassman who's still in classes, and I realized I don't remember some of the topics we covered in class because I have just not needed them to do research.
Yeah. That makes it's good to have discussions too, with your colleagues, because then you actually do get to retain some stuff.
It is very much use it or lose it.
I remember learning about Minkowski space-time curvature and stuff like that.
Yeah.
From talking with a friend, and he was very enthusiastic. He was like, "Guys, we need to learn more about all these things, and we don't have a program here, and we need to know these things." And I'm like, "Huh?" Whatever you say. But he was also a math dude, just with me, and it was really funny to just be like, "Oh, you sound like a nut. You sound like you lost your mind, my dude." Like in proper physics, you know somebody that like knows too much. It's really funny to just be like, "Oh yeah, guys, did you know about this thing?" And it's like, we haven't covered that yet.
Yeah.
You know about this thing?
It is funny. I will throw a bit of shade on physics people and to some extent myself included, if you meet those people, there is a decent chance that you can ask them like, oh, how do you calculate this really obscure thing, and they can just go right off. But then you ask them, how do you change your car's oil? And they'll just stare at you.
You're like, why do I have to do it?
Or like, yeah, or like, how do you file taxes? And they're like, you have to file taxes?
Yeah. That's always been my experience. That's probably why I didn't get along with the physics people, nerds. But very different approaches. Very egotistical as well. Because yeah, the classes are hard, but that also meant you got a big ego. You're like, guys, you don't understand. My class grades me out of 50 as an A. 50% an A. So
if it's like, any consolation, any of the condescension they gave you guys was just simply left over from the condescension they give their other physics majors.
That makes sense. Yeah. It goes hard.
Yeah.
Let's see. You're checking out that video real quick, right?
Oh, did you send it to me?
I'm sharing it. I'm playing on loop. So what's cool about this one? This is a Blender project, and I scripted the math of it. So I had to take actual like numbers and basically create all the variables myself. So however big it is, how long it is, and stuff. It's actually really cool. And let's see, formula for pendulum. The next thing I wanted to try was to figure out how to do a double pendulum, but of course that's significantly harder. Or at least like have it baked in some way. So,
yeah.
it would calculate it all, and it would hard animate it, which is like, and this is hard animated as well. Every single keyframe is calculated. So, which means that everything has like thousands of keyframes.
Jeez.
But yeah, I think I still have this project somewhere, but it was a good test when I tried it.
Are you gonna work OBS?
It's okay, just share all our personal details.
Yeah. No, I mean, I have it popped out. Oh, this is a wave pendulum. Yeah. Oh, that's funny. You coded one. I got to make one in undergrad.
Really? Well, it's still a little scuffed.
Yeah.
It's still a little scuffed, but like some of it doesn't mind.
My chat could see it, but OBS is borking.
It's all good. But I really like this one because it was a fairly easy implementation.
Yeah. Oh yeah, it's a very fun demo to do.
Yeah, I have a friend actually who does a bunch of MATLAB. Like he got very popular. I mean, like very popular.
Oh, there it is.
Like millions of views and million subscribers and stuff like that. I knew this dude from like band of all things. Specifically drumline though. I met this dude and he popped off. He did a bunch of those satisfying pattern videos, and they're all in MATLAB and stuff like that, and he did it because he knew how to code it up. So I showed this to him and he's like, that's really cool. So like an actual friend I know, IRL.
No, this
blew up.
Yeah, no, this is still impressive to have coded, because these are, yeah, you have to basically track, was it 7 or 8 pendulums.
I can probably pull up the project, but yeah, this one was really cool. Because again, it was hard coded. Honestly, it's just the simplest way I can describe it is just generating your data is all you need, and then all you have to do is keyframe it. So you assign the keyframes to the models, and you can, if there's any questions I had about it, like it had a console, right? You do anything and the console will like just display it, what function you just did and stuff like that.
Yeah.
So that's what I would end up doing, was just like, okay, I don't know how to do this. Use a keyframe. Oh, it's an argument with like 70 different parameters. But it's overloaded, so you can just use like 3. So that's what I would do. It's really cool. So yeah, so basically just generate all your data, and it saves to like a notepad, if you will, and then all that data gets interpreted for angles or whatever specific thing it was for. It was the angle, right? At the end you get, it's the formula for the angle. Not dependent on mass.
It is not, no. Well,
of course.
For simple pendulums, yeah.
Simple. Are you saying that it has momentum or something?
No, by simple pendulum, I just mean it's you treat it as an infinitely thin rod and just like a point mass at the end. If you had a pendulum with some size to it, I believe it does become dependent on the mass.
I see. That makes more sense. But yeah, I really like this one, and I had a fun little video sound with it. Let's see, I'll hide that now. Yeah. Really cool. But that was.
I mean, it's a really cool principle.
It's so cool. One of the few projects that I did that was actually like a demo. That's what I kind of wanted to do, more stuff like this. But the amount of effort for some things will be kind of hard. So,
yeah,
here it is. The original one was actually a Newton's cradle. That's what it was. The original was a Newton's cradle. Let me show you that then. I totally forgot about that. And it's like fake. It's like a fake Newton's cradle because it doesn't actually push momentum through. It was. Yeah. It was all just visual fakery. Let's see. Do I happen to still have it? Let me look up Newton figs. Because I rendered it as well, and like it looked really pretty. Shoot, I'll have to share it another time. I don't think I'm gonna find it right now. But yeah, one of many things that I did was pretty cool. But all this to say, we got very off track from the original dude, right?
Yeah.
Shoot. That's us winging it without a presentation prepared, so whoopsies. Alright, let's see. Let's go back to...
One thing I did want to...
Yeah, go ahead.
I was going to say, one thing I did want to talk about Fourier transforms is that when you apply them in physics, it preserves... It's the only way to preserve causality and causal relationships in physics, which is kind of important. So, in physics, there aren't always strict axioms like there are in math, because physics is very much descriptive. We go based off of what we see in the universe. But because of that, one of the things we do tend to require of our equations is that they are causal, right? We experience a strict progression of cause to effect, right? If I drop a vase, it doesn't shatter before it hits the ground, right?
Oh, maybe surprised.
And so...
I'm just kidding. Yeah.
Okay, unless some external force happens to... But yeah, you can't... As far as we know, you can't time travel, yada yada yada.
Not yet.
And so the Fourier transform allows us to express this kind of causal relationship for some things.
Okay.
For instance, when we talk about the susceptibility of a material, which is it's kind of the resistance of a material to change its internal electric field, or what we call the displacement field. And so the displacement field is proportional to the susceptibility times the electric field. And so let me pull up. Yeah. So if I write it out in the frequency domain, because like I said, so the susceptibility is also related to the index of refraction, which, as I said earlier, is much easier to express in the frequency domain. So if I were to write out the displacement field, which is D...
share your screen again?
Oh, yes. Like you said. Let me...
I think my stream settings are stuck.
So many windows open right now. Okay. Yeah. So we have d of x and omega, which is angular frequency rather than linear frequency, but they're basically the same thing. Chi, or not chi, sorry, epsilon, which is the permeability of a material, which is dependent on frequency times the electric field.
Okay.
And so, if we want to say express this back in the time domain, so if a Fourier transform takes something from the time domain to the frequency domain, then there must be something called the inverse Fourier transform that takes us back to the time domain, right?
Yeah, of course.
And so, I guess I should probably write out the Fourier transform in general. So the Fourier transform, in general, f of omega.
Which one are you going
be equal to, and some, I'm gonna use the 1 over root 2 pi just because that's what the thing I have up uses.
Oh, okay.
Your coefficient out front will vary depending on how you normalize it, but whatever the important part is whatever's in this integral. So f of t times e to the I omega t dt, right? So this is basically saying, so an integral is a fancy calculus way of adding a bunch of things up, right? If you remember back to like Riemann sums. So this is basically saying, let me chop up my time domain function into a bunch of different little sine waves of frequency omega.
Show it on you screen because you haven't hid the pendulums yet.
Oh no, it's my internet's being bad. It's lagging.
Oh, is it? My computer completely fried, so I think my end of the stream is also scuffed. I'm like, dang. Yeah, I think I have really bad
okay.
signals broadcast. Probably reset it.
Well,
or maybe it's because it's
fuck it, we'll do it live. Okay.
Do it live. Do it live.
But I mean, can you see it? Or is even my Discord stream share still? Can you see it through my Discord stream share?
Let me take a look at now because I didn't know you were sharing from there. Yeah, I can see it there. There you go.
Okay, so yeah. So if I use this, then the inverse Fourier transform, if I want to go back to the time domain, will be 1 over root 2 pi negative infinity to infinity of f of omega. And this time we invert the sign of this exponential. And the reason we invert this sign is because if we apply the inverse Fourier transform to the Fourier transform, they will cancel out and just give us the original function back.
Yeah, I see it.
We typically like that of linear operators. And so, okay, so yeah, let me apply the inverse Fourier transform to this displacement field.
Let me see if I can share that as well.
So, d of x and t is equal to 1 over root 2 pi integral from negative infinity to infinity of, not chi, I have to stop writing that, epsilon of omega e of x omega d omega. Yes. But also, just applying the just applying the inverse Fourier transform to the displacement field, at the same time, this statement should also be true.
Oh, okay. Yeah, they're tied, right?
Right? This is true because math. This is true because of physics reasons. And so these two right-hand sides have to be equal. And so, oh wait, did I remember to write the, no, I did not remember to write the exponential. E to the minus I. There we go.
Mm.
And so, and then again, this is also true for just E of omega, if I just swap these out, right? So let's substitute in the electric field inverse Fourier transform up here. So that would give me, and I'm going to drop the position dependence for now because it's not important.
Oh yeah.
1 over root 2 pi. You have, and then if I substitute in the electric field inverse Fourier transform, I get epsilon of omega E. Yeah, this is the yes, okay. This is the forward Fourier transform of.
So why do we always have to go
E
between the two?
Why
do we always have to go between the two? What's wrong with just sticking with one? Don't we just transform it and that's it?
So sometimes you still want to know the time behavior as the end result. It's just easier to calculate it in the frequency domain. Like for instance, let's see, what's a good example? Like signal processing again. If you want to receive a wireless signal, but then like play it on a speaker, you need to reconvert what you just received back into a time domain signal so you can play it as sound.
Okay, that's right.
Right.
That's right. So it's just making sure that you can go between the two. That you can do. You're not losing data doing the two, or anything.
Yes.
Got all those frames still. Modify.
Oh yeah, I hate when OBS does that.
What? Is my stream key scuffed? There's no way. Everything. There we go. Rip bozo. Dang. Yeah, we should have prepared a PowerPoint or something a little better, shouldn't we?
Yeah.
That's still fine though. I like talking about these things out loud. It's like the coffee stream I did with what's on the other day. It was just chill. We were just talking about stuff.
I mean, I do just like kind of, yeah, I do just like kind of rambling on about, yeah, stuff.
Oh, like there's something extra scuffed with the settings. What happened? I don't know what else I'm like running on the scene. I'm like, what else is wrong?
Oh my god. I am down to like 1,000 kilobits per second. What the hell? I tested the internet before stream started. It wasn't that bad.
Yeah. Worst case scenario. Dang it. Like it looks like it's trying to record well on my end. Let me also close this real quick. I need a better system. I built this PC myself with some of my intern money from the one trip I did in New Zealand.
Cool.
That was when I was doing the plasma sim research.
Oh yeah.
That was sick. So with that money, I ended up I'm still running fairly light. Like I'm not sure what specs you have, but I have a 1660 GTX 1660, not a super, just a normal GTX 1660.
Oh, I also have a GTX. I think it's a 1070 GTX. So yeah, like that's like, so I got mine for free, my rig for free from a friend, and like that's like the only thing that isn't future proof at the moment, because I upgraded the RAM. I swapped the RAM out. I swapped the cooling, the AIO out, because that was kind of struggling.
Yeah.
It's it's just the GPU.
Let me.
And then of course I can't fix my internet.
Yeah. The internet is sadly a thing that it cannot be fixed. Or can it?
Yeah.
Okay, video's back up.
I wish I could make my own internet.
Well, surely you can, right? What does it take to run the internet? To create your own internet cables and stuff like that?
Well, funny enough, that is precisely why I looked up the orthogonal frequency mixing thing for Wi-Fi, was because I was like, I got frustrated with my Wi-Fi because even, I mean, my internet worked fairly well yesterday, but I was still like kind of I was kind of annoyed. So I was like, all right, what if I just do it myself? What if I make my own internet?
Right. Yeah.
And yeah, it's complicated.
Oh, that sucks. Wait a second. British dominance of the early cable.
One of the very interesting things I've picked up from my research group, from doing what I do for research, is that I have realized that there is a lot more that I can actually do myself than I thought I could. Like, I've had to fix so many things in my lab where it's like, yeah, no one knows how to do this, but here's the manual. Have at it.
Yep. I had to fix the 3D printer.
I had to take apart a... Oh yeah, our 3D printer's busted in our lab. I fixed it once and then it broke again.
Nice.
It's garbage though. But no, I had to swap out... I ended up accidentally stripping an attachment threading on a cryostat, and I had to basically take out half of the inside of it just to replace it.
Ooh.
That was not a fun day.
Nothing like playing with expensive lab equipment, am I right?
I mean, hey, when I get to use the fridge, that's fun. Those are fun days.
Oh yeah. Wait a second, am I still on collab? Hold on.
I think it still says... Oh, no, shared chat ended for me.
Okay, that makes more sense. That's, let me also, like, stream together again? Could you send it to me again, in some way?
Yeah, you could... Yeah. Oh. Well, okay, it still says you're collabing with me, it just stopped the shared chat. I guess because you stopped streaming.
Oh.
So are you online again? I can...
Yeah, my settings are working now. When in doubt, it's because of physics reasons. Yeah,
fixed.
This is a physics phenomenon.
Yes.
Because I saw Tyler and I'm like, I gotta I gotta see him. I need to see him. Wow.
Yeah, I'm sorry, people. I have not been paying attention to chat at the moment because this has been a very good reminder that both of us are fairly new to VTubing and collabing.
Yeah, I feel like and this was like a topic that we both wanted to cover and talk about, and it was just like still very much like when we don't have a plan.
Well, yeah. Well, the issue is, and the reason why I didn't want to make a PowerPoint, and the reason in general why I can't force myself to overly prep for something is, so we have our like document, and I have bullet points of the topics I want to cover.
Oh yeah.
But it's not like it's not a script, because I will never follow a script. I will always end up just, because of circumstances, just in the moment, phrasing it differently or doing it in a different order. So like, it's not worth the effort for me to script something out.
Right.
So like, the document I have is about as detailed as I'm gonna get.
Yep. That's totally fine. And then I did want to contribute a bit about just stuff, but I figured we did a lot.
The stuff we rambled about was educational.
Yeah, no, it's still good. It's like, it's fun. So I enjoyed that bit. It's still good. Okay, let me try to get back on my Gmail. What's the deal here? So I can actually pull up the document as well, because I totally had it here the entire time. Womp, 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 womp. Well, that's not the right one. Wait a second, it was a dots, wasn't it? Yeah, I dig it though. This, right now I want it today to be like a really chill, just vibe. So, after everything yesterday, it was super high energy. So I'm like, man, I gotta chill. I'm gonna relax, you know?
Yeah. Yeah, I mean, yeah.
Oh, let me ask you this.
That's why I like doing both.
Go ahead. Sorry.
Yeah, I was just saying, this is why I like doing both gaming and these educational things, because I do like both in equal measure. There are times when my brain is like, oh, I don't want to think about physics, or I'm gonna punch something, or there's like, all right, I wanna do something productive and talk about things that I'm passionate about.
Yeah, we're chilling, and you do want to cover the things that you want.
It's a coin flip with me.
Yeah, I think physics stuff is a little different for me to like try to demonstrate, because there's so much like actual visuals you can do with it, that I get overwhelmed. And I'm like,
yeah, and
or you need hardware.
Well, even and
equipment.
It's hard in my it's hard in my area of physics specifically to show like VTubing. It's very much a similar issue to NEP, where it's like I can't like bring you guys into my lab to show things off, and a lot of the things that I want to talk about I can't buy with my own money because it's expensive.
Yep, that's where you offload it, and you have someone else host it, and you steal it from them, and then you say, hey, I did this, right? So you get to play with their toys.
I mean,
and
I did ask my advisor this morning if I could use like a scan that it wasn't part of an experiment. It's just a scan I took to align something. So it wasn't going to be used for a paper or anything. But I was like, oh, it'd be cool to show off like a real example of like FFTs. But no, apparently there's the risk of like university red tape, and I was like, that's not worth it.
That's lame. Yeah, if you can get sponsored by your lab to like, I'm gonna try my best to, because I'll probably just like, once I get back to university, my idea is to like just literally go and into the different departments and harass them and be like, "Hey guys, what's up? I'm here. Can I play with your toys?"
I mean, I would love to do that, except for the fact that I'm pretty sure that the university would impose the condition that you have to like cite the university, and you know that would dox me.
Yeah, fair point. That's what you'd have to just not tell them, just sneak around.
Yeah, I honestly could have, because like the graph that I wanted to show, it has no identifying information on it. It is literally just if you threw out a plot in like matplotlib in Python, it looks like any other plot.
Yeah, really. So it just because of the data it uses.
I guess, yeah, because the data was taken on campus with university computers and equipment, and yeah.
Nonsense. That's not ethical. To cite your sources or anything. You don't have to do that. Just make it up.
Well, it's not sources, because if you're talking about like citing the source, like who took the data? I took the data.
Yeah.
My source is me.
Yeah. Well, still though.
That's why I thought it would be fine. I'm like, as long as I'm not using it for a paper, like I'm not using the data for a paper, so there's no risk of someone stealing the data. But like I said, it wasn't worth the headache of trying to argue with the university.
Yep. I have a question then, real quick. I have a question. So, relevant to still the Fourier stuff. So, the handiness of the Fourier transform is that we can get packets of information in a medium, usually wireless technology, or it could be really anything, and deliver it and then still interpret it, right? It's still able to be like read. However,
yes,
the issue is the original method, the method, is fairly slow, right? Fairly computationally heavy, right?
Yes.
Now, what's the deal with that?
Yeah.
Why is there this whole other thing here talking about a FFT? Or a fast Fourier transform. Kind of like to tie it a bit.
Yes.
Why can't it just be Fourier transform? You know, I don't do fast math. I just do math.
Yeah. Well, funny story about how we developed the FFT. It was because of the Cold War.
Oh.
So yeah, like you said, the original Fourier transform algorithm was very slow, and in the 60s we wanted a way to kind of observe or track whether or not underground nuclear testing was going on.
Yeah, because if we can beat the Soviets.
The way they thought to do it, yeah. And so the idea they had was, all right, if someone's doing underground nuclear testing, it's going to cause seismic activity that would be different from a normal earthquake or something, right? So it'll show up as different set of frequencies than some natural tectonic motion or something. So, all right, so you can use a seismograph, right?
Okay.
But again, they needed a way to isolate the frequencies coming from a nuclear test and, you know, normal geological activity. And they needed to do it fast, because if they did all that transform by hand or using the original algorithm, you know, there was just no way to keep up with all the data coming in. So the algorithm, which was named after the people that developed it, the 𝖘𝖔𝖈𝖎𝖑𝖘 FFT was the original FFT algorithm.
Nice.
They managed to reduce it to order n log n.
Yeah, I noticed the original here. It says it was n squared. So yeah, n log n is significantly better. Let me observe that as well.
Oh.
What?
Oh my god. What? I hit my follower goal.
Oh, hey, good job, man.
I didn't even see who followed me, but thank you.
Yay. Let's go.
I do appreciate that I did hit it on a smart stream.
on a smart stream.
And not my usual dumbassery.
Which, by the way, how's files going? Or the
Files?
the paranormal file. What was it
Oh, okay. Somnium Files. So I beat it off stream.
Nice.
Because, yeah, because personal reasons. But yeah, I did beat it. I should go back and to where I left off and play through it again because I feel bad.
Do what you can. Do what you can.
But it was a very good game.
Nice. Let's see. Oh, I'm looking at n log n. It is significantly better than x squared. Yep. That is really good. So if I can express how much better that is, it's yeah.
Oh yeah, because I'm not a computer science person really.
Yeah.
All I know is n log n is slow.
Yep. So let me express it as it is functionally linear. Kinda. Not really, but like the scale factor of log n, like log x, right, is pretty good, right? Log x, yeah. Right? It means how many digits does it have, right? So if I had like a number 500 or something, it's like 3 digits. 500 has 3 digits, right? So by the time it hits 1000, that's 4 digits. So that's the scale factor, 3. Then by 1000 it's 4, and then by 10,000 it hits 5. That's the scale of log x. Like that's how slow it is.
Okay.
And then obviously x, because it's 1 to 1. So yeah, that's actually really freaking good. So the scale factor of log x is actually really not that bad, like at all. So yeah, no, that you can scale like that. That's kind of cool. That's really good. Yeah. And if you look at I'm looking at a graph of x squared and then x log x and then x. That's really freaking good. Wow. How do they do that? 𝖘𝖔𝖈𝖎𝖃, do tell, what done you do? Tukey. Yeah, it says here that they had a version. Gauss, apparently, the Gauss, had a version that was coming out he developed a fast algorithm for DFTs, but it was unpublished. It was talking about like asteroids and stuff. We also wanted to interpolate.
Yeah, I did notice a lot of the. Yeah.
Hi, ads.
I did notice that a lot of the history behind the Fourier Transform was to do astronomy stuff, but unfortunately I am not an astronomer.
I don't like looking up.
I think space looks cool and pretty, but that's about it.
Yeah, that's it. I'll let them play around with it, because it's just a bunch of data analysis at that point.
Yeah, that's why I moved away from doing experimental particle physics. It's all comp sci. There's no physics.
Yep. And as much as I did comp sci, I did a full degree in it, I happen to have my own opinion of it. Like, yes, you can do it. But it's like... Yeah, it's all AI now too, so...
Yeah. But yeah, I like doing just enough coding that it's not full-blown comp sci. Like, the amount of coding I have to do in my research group is the sweet spot.
Nice.
I just type up some Python codes. I don't have to worry about it being efficient, and I'm fine with that.
That's good. Oh, here's an unsolved problem.
But okay.
Unsolved problem in computer science. What is the lower bound on the complexity of fast Fourier transform algorithms? Can they be faster than big O of n log n? Actually, there's a whole list here of unsolved problems. Well, of course, PNP problem.
Oh yeah.
Polynomial versus non-deterministic polynomial time for specific algorithmic problems. Interesting. These are computer science questions. Okay. A lot of it like conjecture. The lower bound of FFT. So yeah, because FFT is in big O of n log n. So that means that and the original algorithm was n squared. So can it be better than n log n? Which looks like this. This is x, this is n log n, and then this is x squared. That's really cool. When I was covering some of the multiplication methods, I thought it was really cool that some of them have really optimized multiplication algorithms, right?
Yeah.
There's a whole article about it. It's so cool.
Alright, I finished. Alright, I do want to talk about causality. I finished writing it out.
Oh, good. Okay.
So, because most of, at least the people watching my stream, aren't going to be able to follow the math I just did, I just want to focus on the result. So, your displacement field, your D of T, you have your linear contribution, just epsilon naught times E. It's this part that preserves causality. Because this G of T depends on your material properties, right?
Let me share.
And typically...
Am I? In fact, already. Yeah. Okay, go ahead.
Alright, and typically the material properties are such that this kernel function G of tau, where tau is the difference in time between the source, your electric field source, and the time that you measure it. So typically, I believe that should be flipped. I think that's T minus T prime.
You got an error. You spelled something wrong.
I think I just have a minus sign error. No, I think I just have a minus sign error, which is par for the course for me. Yes, it's T minus T prime. Okay. Okay. Because, right, T prime is the time of the source, of the field. And T naught prime is the time that we measure it at. So typically our kernel function, our material property function, is such that for tau less than 0. So for tau less than 0, right? So for T prime bigger than T, right? So measuring it before it even shows up, right?
Yeah.
You don't want that. So usually that's equal to 0 for tau less than 0.
Makes sense.
And it's equal to some function for tau greater than or equal to 0. And so because of that kind of piecewise property, this integral from -infinity to infinity of time gets cut in half. And so you're left with the integral from 0 to infinity of G of tau times E of T minus tau.
I think I remember this bit. Yeah.
So only the contributions coming when you measure after the electric field has already arrived in the material or has already affected the material actually contributes to the overall field inside the material. And this is only really true because of the nature of Fourier transforms.
Okay.
If you were to do like some other transform, you wouldn't be able to get back that convolution integral. So like this is technically a convolution integral, but it pops up because of because we implemented these Fourier transform definitions.
Oh, I see. So with that gives us a chance to, well, what does that bit do exactly? That the g of tau, not the constant. What'd you call it?
The g of tau is just it's a function that's entirely based on the material properties. So it's epsilon, which is the permeability, the electric permittivity of the material, in over epsilon naught, which is the permittivity of free space.
Oh.
So this is just a function of your material entirely.
I see. Okay.
Whatever medium you're looking at. Yeah.
So like material wise.
So
like
yeah, you
metal,
only propagate the. Yeah, like if you're looking at a metal or an insulator or air even counts. Air has a permittivity.
Okay. The permittivity of your mom.
That does exist, yeah.
I'm funny. That's interesting. I now you don't often have to calculate these by hand anymore, right? But if you had to,
no. Well, maybe in theory. At least in experimental, I don't have to do any of this stuff. The calculations that I do in experimental are literally just take an FFT, divide some things out, and yeah, do some algebra.
I see. That's not that bad. It's actually really not that bad. The only issue is those integrals. The integrals are pretty nasty.
Yeah. Yeah. But usually, if you have to calculate them, usually you can throw it into a numerical solver, like MATLAB or Mathematica, because very, very rarely do you get whatever's inside that integral to be nice and behave properly.
Also, hi Nep.
Oh, hi Nep.
Nep has made it.
And then also, did you know that the Fourier transform can be derived in quantum mechanics?
What? Wait, why?
Yeah.
Because of the...
You don't because of the way linear algebra works. So, yeah. This was the other thing I wanted to show off. Yeah, you don't have to assume the Fourier transform. So let's say I have some state psi, right? So in quantum mechanics, this just represents the state of whatever particle you're looking at, right?
Okay.
And if you took linear, right?
Yeah, of course. I took it kind of like functionally three to four times.
Okay. Yeah. Right. So if I have like an eigenstate of an operator, that just gives me back the eigenvalue.
Right.
And I can do the same thing for momentum, and I get P times this. And then the other thing you need to know is that if I wanted to apply the momentum operator to a position eigenstate, that is
gonna be 0, right?
I h bar ddx of x. Yeah. I'm not going to derive that. There's reasons behind it.
Derive it right now.
Just trust me.
Solve it all for me right now. Do it everything right now.
I can. All right.
No.
So, I mean, if you.
Okay.
Right. So.
Hold on. The chat also wants.
So okay.
It's up to you. It's totally up to you.
Do it now? I mean, I can. I mean, it's not that long. It's literally just taking an approximation again.
Okay, then do it.
So,
and then I can read. It says here.
So in quantum mechanics, you have unitary operators. So unitary meaning the inverse matrix is the Hermitian. No, yes, is the Hermitian conjugate. And so if you want to move a particle in space, right? So let's say u of x prime on psi of x. This gives me psi of x plus x prime, right? I have applied this translation operator and moved the state x prime amount.
Unbelievable.
And so this operator is in fact equal to e to the minus minus I p hat x prime over h bar. And so I can approximate that as 1 minus I p hat x over h bar. And I can also approximate this using Newton's method as psi of x plus d dx of psi of x at x prime. And so by comparing the two sides and canceling out, I get this thing.
Oh, okay.
Yeah.
That makes sense.
But yeah.
But
okay. And then the other thing that's important is that if I project the state vector onto a position eigenstate, this gives me the wave function.
Oh.
This is not lambda. Okay.
Pretty neat.
So, you know that if you have a set of eigenstates, a complete set of eigenstates, I can make the identity matrix out of it, right?
I think so. That makes sense. Yeah. I haven't done that end of it, I think. So, do tell the process.
So because momentum is a continuous variable, when I add up the projection matrices of the momentum eigenstates, it becomes an integral. So if I add up all your momentums, negative infinity to infinity, this gives me the identity matrix. So this would be an infinite amount of ones on the diagonal.
Oh, just call that the Kronecker delta.
No, not quite.
I know.
That the Kronecker delta is a bit different because that's not a matrix in quantum.
It is not.
But okay.
Interesting. Actually, I found that out.
But so psi onto x is equal to x times the identity operator times psi, right? If I the identity matrix just multiplies it by 1 essentially, right? So does that still track?
Yep, that sounds good to me.
Alright. So if I substitute in our formula here, I get negative infinity times x p prime psi dp prime.
Okay.
And in the same way that I defined our position space wave function, our momentum space wave function is this p prime times psi. And so and this x times p prime is, again, for reasons, e to the I p prime x over h bar.
Okay.
So if I substitute both of those in, I get that psi of x equals integral from negative infinity to infinity of psi of p prime times e to the I p prime x over h bar dp prime. And that is just the Fourier transform.
Ah!
From momentum to position.
Interesting. That's actually
Yeah.
fairly easy
So
to get. Gonna pop up a lot then, huh?
in the same way that time and frequency are Fourier conjugates, position and 1 over wavelength are Fourier conjugates. And in this case, momentum is Planck's constant over lambda. So since you're only changing it by a constant, momentum and position are Fourier conjugates.
Yep. Okay. That makes a lot of sense. And you
So
can
yeah,
find a
I
bunch
didn't
of conjugates.
assume the Fourier transform. Yeah. Yeah, time and energy are Fourier conjugates for the same reason.
Hmm. So you didn't exist. Fourier made it up then. He didn't discover it.
I mean, he did make. Well, he made up the series.
Fair point.
He created the series to serve as the solution to the heat equation.
Everyone's trying to solve the heat equation.
Yeah.
But that's very interesting. So I wonder where else it pops up from. Yeah, 𝖈𝖗𝖊𝖉𝖎𝖙𝖘. The momentum. That's right. I wonder what these some of these scientists ever did, and you know, after they did it, how well their success was, and what they end up, how life was after the fact. You know?
Yeah. Some managed to like discover a lot. For instance, let's say in physics, Einstein's a good example. He did a lot within his life.
Yeah. Stealing stuff.
Keep in mind, his first discovery was not special relativity. It was Brownian motion.
I thought it was the photoelectric effect. No, he got a Nobel Prize in that.
No, that's what he got the Nobel Prize in. But his first like major breakthrough in the field was Brownian motion. So like the random behavior of like microscopic particles bouncing into each other. Like if you look at pollen under a microscope and you want to track how it moves, that's Brownian motion.
Oh, I see it. I've seen this before.
But in contrast, like, have you heard of the Higgs boson?
The Higgs boson?
Yeah. The God particle. So the Higgs boson, the theory for it was developed by Peter Higgs. But that's about all he did in his career.
Oh, that's it. Oh, okay.
Yeah, he was never able to make another like truly significant contribution to the field.
That's a bummer.
And again, it's nothing, not a statement against his intelligence. It's just it is kind of random what or when a discovery happens, right?
Right.
Sometimes you just need to have like encountered the right kind of research, the right kind of talks and seminars, and something comes to you.
Right. Or someone shares an idea and you know the immediate next consequence, or you can work on it on your own. Yeah.
Yeah.
That's interesting. It's a lot of like usually just exchanging ideas that people just, oh, did you hear about this?
Yes. Physics.
Yeah.
Yeah, physics is very collaborative. A lot of, at least like experiment. I could not do my job without like at least 2 other groups, because I study materials, but I need someone to grow them first. I don't know how to grow them. That's almost completely different physics. So we usually have to cooperate with like a growth group that is willing to grow these samples for us.
Right.
and then they'll send it to us, and then we analyze it for them, and we both share credit on whatever paper comes out of it, hopefully.
Yeah, you usually like, hey, I did this, you can do this step, you can do that step, and
Yeah.
that's usually pretty streamlined.
Yeah,
That's
it's
actually
like,
really
well,
cool.
yeah.
Let me see. Let me tell you a bit of cool stuff about like a dude. You know how like infinity became popular, like as a discussion point, as an actual like taken seriously, and the concept taken seriously, because people, of course, like the layman does not understand infinity at face value, right? But like,
Yeah.
imagine that, but like all of like math, all of physics and stuff, still.
Yeah.
Are you familiar with like the people you know about 𝖘𝖔𝖈𝖆𝖍𝖎𝖙𝖘 and 𝖘𝖘?
Unfortunately, yeah.
I love that story. It's pretty interesting. So, once upon a time, 𝖘𝖘 was just doing some infinity stuff, and then 𝖘𝖘 was like, "Oh, hey, we should be friends. I'm also doing some infinity stuff. We're gonna make everyone take it seriously." And then 𝖘𝖘 showed him some of his work, and was like, "Yeah, this is pretty cool, isn't it?" And then 𝖘𝖘 was like, "I should publish this in a paper. I should get really popular for this." He really wanted to fit in, and then sure enough, he broke 𝖘𝖘's heart, and he had to be a lot slimier to be taken seriously, and then he ended up.
Oh, I did not know that part.
Yeah, he plagiarized a bit of his work, because 𝖘𝖘 didn't really publish anything. He was a really chill dude, older dude too. And then 𝖘𝖘 was a much younger dude. It turns out he broke 𝖘𝖘's heart, and they stopped talking. And then after 𝖘𝖘 he couldn't really get into the German mathematics, science, whatever thing he really wanted to be a part of. That everyone basically like was in a group chat without him, if that makes sense. And they made fun of him, and they called him stupid. And yeah,
Wow.
𝖘𝖘 ended up dying. He was kind of depressed by the end of it all. And then 𝖘𝖘 did his own thing.
Yeah.
And then after that, the kids started using.
I remember. Yeah, I remember. There's a similar story behind like Newton and Leibniz, which is even more it's even sadder when you consider the fact that when Newton developed derivatives initially, he thought you could only take time derivatives. He did not think that position derivatives or any other derivative could exist or be calculated.
Oh, really?
But Leibniz was the first one to say, well, these derivatives and integrals, because he actually started he started developing calculus from integrals. Newton started with derivatives, but Leibniz started by actually just applying it generally, like any variable, any continuous variable, you can take an integral of, you can take a derivative of.
Okay.
But because Newton was had contacts with the was it the Royal Academy of Sciences in Britain?
I think so.
His paper just became a lot more widely known than Leibniz's, and so Leibniz, I believe, got accused of copying Newton.
Oh no.
And it was only, I think, after the fact, when people looked back at their respective notes and papers, that they realized Leibniz was actually not only developed it independently and didn't like plagiarize Newton, but like was honestly kind of on the closer track to general calculus. Or like a general theory of calculus.
Right.
Not just time derivatives.
I think there's a fundamental theorem of calculus, isn't it? Chat Lano says, apparently Leibniz was a much chiller guy compared to Newton. At least according to Strogatz, they had more of a student-teacher relationship, with Leibniz asking Newton for help, to which Newton would begrudgingly do so. That's crazy. I believe it.
Yeah.
Look up Newton. They were friends, right? Maybe.
I believe they did start their communication friendly, or at least not on bad terms. Because if I remember correctly,
Euler.
I probably should. I'm not going to say this as fact. This is just as far as I remember. Newton's work on calculus came later in his life, so this was kind of when he started getting into like the mysticism stuff, and he got fairly paranoid towards the end of his life, and so I wonder if that contributed.
I wonder. That seems like even back in the day, everybody was just trying to. If you weren't chill, you had an objective, especially in academia.
Yeah. I mean, I told you about this privately, but yeah, in Italy in the Renaissance, universities didn't have tenure. Rather, at least in mathematics, if you wanted a professor's position at a university, you could challenge them to a math duel, in which you presented a problem, right? And if you could come up, if they could not come up with a better solution than you could, then you got their position.
That's crazy.
And I believe that is the reason the Cardano formula was sat on for like a couple years at least, because I believe Cardano found the solution, but he wanted to keep it in case someone came for his job.
That's crazy.
So he didn't publish it initially.
Cubic equation?
Ayo, math duel?
Is that the finding third roots? I'm sorry, yeah, finding not third roots.
Yes, yes.
Cubic
Cardano
roots.
formula. Yeah, for cubic solutions. Yeah.
That's crazy.
Yeah, Newton is him saying, "I'm not being done," and he's receiving a letter from Bernoulli concerning the Brachistochrone. Oh. I didn't know Newton did work on the Brachistochrone.
That makes sense. It's a spinning cycle. I could make a visual of that.
Yeah, but at least the way it's taught nowadays, it's very much an exercise in the calculus of variations, which did not exist at Newton's time.
Oh, so for what purpose did he need the Brachistochrone? Well, hold on. No.
I mean, like the motivation behind, like principle at least, the motivation behind calculus of variations definitely existed back then. Like there were instances where you wanted to minimize a function or minimize like a functional. I was just saying like the math did not exist back then, so I didn't know that Newton had worked on the Brachistochrone.
That's interesting.
I know Fermat was able to show an optical analog to the Brachistochrone. Light will form a Brachistochrone if you pass it through basically an infinite amount of like infinitely thin sheets of glass with varying indices of refraction.
Yeah.
Because of like Snell's law, it will just as it becomes a continuous amount of indices of refraction, the light will bend and form the inverted cycloid.
Oh wow, okay. Cycloids and other things like that. Cool. Showing off the LaTeX feature. Should pop up. It renders on the screen. Let's see.
I also have LaTeX, but it's not even borked. I think I just need to mess with it a bit.
Hold on. Let me try it again. And yours. Huge. 6, 7. Yes. Works on my end.
Yeah, like it works. It makes everything big, not just the LaTeX stuff.
Yeah, you might need to check it out. I can help you with it. It's got some tweaking to do. Let's see.
And then
Snell's law.
Need to tweak the font color too.
Right. So okay, let me ask you this.
Yeah.
So the lens version of the brachistochrome, if I was to phrase it, it's like operating lenses law, or it's lenses or Snell's law. I forgot which dude it is. For
Schnell's law.
Schnell, is that?
Yeah, Schnell's law tells you. Yeah, he was German, so it's the German Schnell.
Schnitzel.
Oh yeah, lenses. Yeah, lenses law with a Z. Lenses law hates you. That's how we were taught lenses law in undergrad.
Why? Because
lenses law tells you about the induced current caused by a changing magnetic field, right? And so the way electromagnetism works is if you have a changing magnetic field, the produced electric field will work against the initial current that generated the magnetic field.
Oh, that's right. That's right. So that's what
So like, if you drop a magnet down like a charged or like a magnetic field tube, and if you'll notice it like slows down a lot, that's lenses law.
That's cool. My buddy works with chillers, like industrial like air conditioners, you know. So one of the things he uses is a probe, which he uses a monitor to identify which tubes are bad or good, and by literally rubbing it into it, it induces a current. So you can get a read on the probe on his monitor. Yeah. So if it has good reads, so you have to test the tubes. You know what to look for. But on the oscilloscope or whatever it happens to be, it automatically detects which things are good or not. You know, because the tubes themselves, they're coiled, if you will. They have like ridges. So the whole point is that the surface area or the path what the water does, it's continuously rotating throughout all of it. That it by the end of it ends up significantly colder than it was when it started. So I thought that was pretty cool. And one of the things he was showing me was like the probe. I actually did a temp job with one of the buddies. It was literally like, hey, I need some hands. Come with me. You'll get paid for the day. I was like, is this under the table? Nice. And he's like, yep, basically. That was pretty cool. I got to learn a lot. I learned about epoxy too. Sandblast epoxy. That was really cool.
Oh. There's an electrician's tool that relies on induction. If you've ever seen like that weird, it looks like a multimeter, but it has like a clamp around it.
Oh yes,
the electricians use it to find live wires. So like if you wrap it around a wire, if it's live, it will induce a current like around the clamps, and then it'll detect that current and say, oh, that's live, don't touch it.
Yep, that's a clamp meter. Yep, because it detects magnetic field.
Yeah,
cool.
Yeah,
really cool stuff. Clamp meter. Invented by, let's discover this. Oh, the Hall effect. It's more sensitive and is able to measure both DC and AC. The Hall effect type.
The Hall effect's more complicated.
Oh boy. Let me see. The visual's very good. Hold up. Looks like you have a current here, and you have a magnet. And when you have the magnet, it makes it. Oh, hold up. Possesses a negative charge on the top, symbolized by the blue color. The positive charge on the bottom. The direction of the electric field in which the magnetic fields are changed respectively, which switches the polarity of the charge around. What? I'm just gonna say it makes the current do different.
So, the way I remember it is, so if you have a current carrying wire and it's immersed in a magnetic field, it will bend the wire depending on where it's pointing. But if you have like a current going through a sheet, it'll bend the current, but because it's a sheet, that bend current now creates a potential difference across the two ends of the sheet. So that potential difference creates a magnetic, not a magnetic field, an electric field. And so
Oh,
that voltage difference can then be picked up. Yeah.
I see.
And then there's like the quantum Hall effect, which I know even less about, and then the fractional quantum Hall effect, which I know almost nothing about.
Yep. Man, Wikipedia is an actual resource.
That gets into knot theory.
Knot theory? Wait, what? How? What is it? Don't tell me like wires and cables and stuff. Like.
No, it has to do with like braiding groups or something. Like I said, that's not my area of research. It's adjacent-ish, so I've seen it in literature, but I do not understand it.
Tell me it again. It was called the what?
The fractional quantum Hall effect.
Fractional quantum Hall.
Yeah, actually, let me pull this up, because maybe something will come to me, because it's been a while since I looked into it.
Oh, there's a section called Impact. I just wanted to say that.
Yeah.
Genshin Impact. Nerd.
Nice. I was playing that earlier.
I saw. And Honkai. I got pretty far. I'm not like level 90 on my characters for a reason. But I was playing for a bit.
In Honkai or Genshin?
Genshin. What do you call it? I have a few teams already, but my favorite one is just 𝖈𝖊𝖎𝖕𝖎𝖙 water spin, and then they nerfed that, I think, but still. And then Wander is just so good for travel.
I wish I had Wander.
It was one of my actual picks. He's so good.
That's why I really like 𝖈𝖎𝖕, because of her alternate sprint. It makes things fast.
Oh, Netland, right?
Yeah.
Okay.
Yeah, I sorry, I don't know when you stopped, or if you're caught up or not.
But
my favorite team.
I'll let you talk.
I was gonna say I have two favorite teams. I have one that I use for every other region, and then I have one I specifically use for like nod cry stuff. If you've caught up to there.
I have not. I explored a lot. I finished Inazuma, and I just got started on Sumeru.
Okay.
In terms
so I
of
won't
story.
spoil the nod cry stuff. But my favorite non-nod cry team is 𝖈𝖎𝖕𝖎, because she has really good electro DPS. 𝖘𝖔, because 𝖘𝖔.
Yep.
She's amazing.
Nice.
Yao, because she's a really good healer, and then Yelan, because of her ult, the dice thingy.
Okay. I wanted to get her so bad. I need water. I need hydro.
Yeah, I need cryo. I have no cryo characters. Oh, well, I have no good cryo characters. Let me say that.
I have Shunha and I have Chongyun, so I have like a auntie kid team.
Yeah, I wish I had Shenhe.
And then the rest I'm still budgeting, so because I'm free. Well, I was free to play for a second. I actually spent some money in quite a bit actually. In Genshin.
The only money I've spent on Genshin was for a skin for Yelan, an outfit.
Oh yeah, I know that one.
That was it.
Pretty good.
I've never paid for character pulls, and I'm completely free to pay on like Uma and Honkai as well. I accidentally got really lucky in Honkai, apparently, as I'm finding out. I know less about the lore of Honkai than I do about Genshin, because one of Nep's mods, 𝖘𝖔𝖈𝖎𝖕𝖎𝖙𝖘, got me into Genshin. So I knew at least a little bit going into it, because I'd been watching his streams. But I went completely blind into Honkai, and I apparently... Because, you know, like, when you first start those games, they give you, like, some invitations where you can just choose some characters to get. Apparently, I just happened to pick the really good ones.
Right, I see. Wow, look at you.
Just because I was like, this character looks cool.
Yeah, they are. I've been meaning to talk to 𝖘𝖔𝖈𝖎𝖕𝖎𝖙𝖘. I think 𝖘𝖔𝖈𝖎𝖎𝖕𝖎𝖏 is pretty cool. But he's an Aranara.
Yeah.
right?
Yes. Yeah.
Yeah.
He is an Aranara.
Yeah. I can do something with that, I think. I'll probably tweak it
I'm waiting
maximum model.
for... Yeah, I'm waiting for Nep to get to the Aranara area. Last she streamed it, she was stuck in Inazuma.
Oh boy. Oh, there are models of it.
Yeah.
Specific, which one though? Which one?
I'm there. Wait, you got to the Aranaras? When?
You could just do it, right? You can just walk.
I mean, okay, no, I know she's explored it. I meant like the story, because there's a. I know you unlocked the map. I meant story-wise, you're still in Inazuma.
Oh no! I just started Sumeru.
Because
So.
Yeah, because I was gonna say like the Aranaras don't show up if you just explore the region. It comes up in the story somewhere.
I thought you just roam around.
That's what I was saying. I want. No, they're not. You can't encounter them in the wild.
What? I must have done something.
There's a reason for that, but that's in the story. You might have accidentally triggered a quest. Actually, can you trigger that quest before getting to? Oh yeah, I think you can. Yeah, you might have accidentally triggered a world quest.
Oops. That sounds way.
I mean, it's fine. I like the R&R.
Oh, I'm liking
I don't want you to get through all of Genshin. I just want to see you play through the Kolak quest.
Stream went down. Okay. Actually, everything's waking up.
But yeah, I'm currently in a period where I'm hoarding gems in Genshin. There are like a bunch of characters coming up at once that I really want.
Okay. Let's see. Yeah, Kolak's more like looks like this one, right? The big one.
Yeah, it's like, okay. You play Pokemon, right?
Yes.
So Kolak's model is specifically an Aranara fused with a Shinx.
Oh.
Like the Shinx, the electric Pokemon from Sinnoh.
Yes. I see that now.
No, it's really cool.
I see that now. I totally see that now. Okay. I can probably grab a model and do something with it if you want something. Stuff like that. That's totally
that
legal
would be
to
cool.
do.
Or just make Nep throwable Kolaks.
That works too. Nep, would you want that? She's playing Animal Crossing.
Of course she is.
Wait.
It's either that or Beaver Clicker.
One of the many. Let's see. I couldn't find anything about that one Hall effect. The fractional quantum Hall effect. I couldn't learn anything about that.
Oh, I have it pulled up. It's so okay. Yeah. Okay. With full disclosure, I've pointed out that I do not fully understand this. So the quantum Hall effect is kind of the Hall effect, but when you have certain exotic materials, electrons can act at the surface of a material like they are two-dimensional. And the quantum Hall effect is if you apply a magnetic field to these like 2D electrons, the conductance, the sheet conductance, only exist in integer multiples of E squared over H bar. So that's the quantum Hall effect. But in even more exotic materials, instead of it being integer multiples, you can have rational multiples, like fractional multiples of. And the reason this is important is because these fractional states do not correspond to boson-like behavior, so spin 1, so like photons, like photons are bosons. So they don't act like bosons. They don't act like fermions, which is like electrons, protons, neutrons. They act like something called anyons, which do weird things and involves topological stuff that I don't understand.
Really? That's...
But if you could make an anyonic state, like if you could prove and detect like an anyon state, I believe that can serve as a platform for quantum computing.
Oh.
Thank you for the hydrate, Tyler.
Interesting. Oh yeah, thank you, Tyler. Drinking water.
I have green tea.
How does this tie in with knots, though? I mean, or maybe not this one.
Maybe I misheard it, but I believe like if you do the theory behind it, it has to do with like the braid groups. Let me see if I can pull it up. It might just be group theory and not knot theory. And braids. I guess I assumed that if you braid something, it must be knots.
Knot
no,
theory.
This is knot theory. Yeah. Braid groups. Yeah, this is knot theory.
Braid group.
Yeah, so... relationship to... okay, I can't. It's not on the Wikipedia page because this is fairly advanced in all fairness. But yeah, so the fractional states have to do with certain braid groups. So like, for instance, fermions, spin 1/2 particles, right? They exhibit SU2 symmetry, special unitary 2 group.
Yes.
Of dimension 2. What that means is they transform a special way under like the Pauli matrices. So I believe what that means is these anyonic particles behave according to these braid group generators rather than like SU2 or spin 1 is also SU2, sorry.
Still though, let's see. Man, I gotta review a lot of this stuff.
Sure. Are friendship bracelets knot theory? Yes. Knot theory...
Is this enough? Hold on. Pull this back.
Yeah, actually pull up. Yeah, so there is literally knot theory in mathematics.
Yep.
Which is very vital to string theory.
That didn't display correctly.
What? Oh.
Dang it. How do I delete my own message? Oh, I know how. You can ban yourself?
What? Oh, I do know I get, like... I think I get notifications that are like, oh, I've been subbed to myself for like 3 months. And I was like, is there a way I could unsub from myself?
Yeah, good question. If you ban yourself...
Yeah, what happens if I use all infinity of... Yeah, what happens if I manage to use up all of my infinity channel points?
You die. It's like breathing. It's like you can't have no air in your lungs ever. That's how it works. I couldn't think of anything. Yeah, there's a lot of like really interesting group stuff with especially braids though. That's so interesting. One of my professors is actually a knot theory specialist. So
Oh.
He had a really cool, and that's actually why I like have the you know, my boots. They also have knots, right? So they're not theory knots.
Oh. Oh.
They're actually like 8 point.
I don't think I noticed that.
Yeah, it's pretty cool.
Yeah, unlike some other VTubers, I did not pay too much attention to the feet area.
Oh. No, I just
when
keep
was
it
drawing the promo art.
Are there any people in particular?
Is it accountable? I probably shouldn't say, not for slander reasons, just because they deserve a break right now.
Oh, okay.
But it's a certain cryptid. This is all I will say.
Interesting. Okay.
I would assume countably infinite, because it's discrete, like it's integers. You can't have pi amounts of channel points, right?
You'll be surprised. I'm just kidding. I don't know what that means. You can't have
Pies.
Technically, there's a computer limit to it. So there you go.
Yeah, I was gonna say, even like you have a finite amount of, or not finite, but like countably infinite at least. Well, no, you still have a finite amount of bits.
I'll give
I
you a bit.
wonder if there's an upper limit to how much I could charge for a redeem.
I'll give you a bit. What do you call something with 4 bits?
I don't know. What?
I believe that's a byte. That's 8.
Yeah, it's 8 bits.
I think that's called a nibble.
Yeah.
Yeah, here it is. A 4-bit quantity is often called a nibble. Yep. Yep.
Oh my gosh! Of course, that's an actual thing.
It is.
Did you know that the imperial unit, so the freedom unit for mass, is not pound. That's a force. It's slug.
A slug?
Yes.
What?
That is the imperial unit for mass.
What? No way. Yeah, I guess.
So I believe one pound is like 32 slug feet per second squared. Oh, thank you for the bits. Get nibbled on. Oh no. I don't have an eat me redeem.
I love this country and hate it in Epsilon more. What? That's great though. There's a bunch of really interesting. Why is a slug though? What is a slug in this term referred to as? History.
I'm sure it has to do with like metal slugs, right?
It seems to be coined in the 1900s by British physicists. These are other foreigners, okay? British physicist.
Okay, but British is different.
British physicist Arthur Mason Worthington.
Blame Astral.
But did not see any significant use until decades later. It is derived from the meaning solid block of metal. Not from a slug.
Although it's a lot more recent than I thought.
Yeah, 1900? Well, I suppose.
Yeah, I thought it would be way old.
Well, most of these come from the fact that,
the inch. Hang on, the inch version of the slug, which is 1 pound foot second squared per inch. Oh my god, that is nasty. Has no official name, but is commonly referred to as a blob. Why? Just why?
Oh, there's no way. That's ridiculous. Dimensionless numbers. What's your favorite dimensionless number?
Dimensionless number?
My favorite ones is a Reynolds number, actually.
I think mine would have to be the fine structure constant. Actually, no, that's not unitless. Hang on.
Yeah. Is that why people refer to bullets as a slug? More than likely now.
No, because that predates the unit. That's what I thought. But no, it predates it.
Oh.
Favorite unitless number.
Hold on. It says here it's a unit associated
I?
a mass that accelerates 1 foot per second squared. Well, no, yeah, still. Yeah, who's got the brain cell right now? Current use in the United Kingdom.
I have to go with I.
It's used on baby bottles.
I like I.
I is pretty good.
Yeah.
A Reynolds number. Look up Reynolds number. Reynolds.
Reynolds number.
Yes. It's pretty.
Oh, that's for drag, isn't it?
Kinda. It's it tells you specific.
Oh, fluid mechanic. Yeah.
Fluids, yeah. It's often to do with like predicts fluid flow patterns. So, but it's a measure between the viscous force and the inertial forces. So, low Reynolds numbers, it's laminar.
I found a list.
And then higher Reynolds number is more
turbulent. I
turbulent.
never took fluid mechanics.
I loved it actually. I didn't.
But, okay,
I didn't take it, but I got the crash course in New Zealand in it. They don't say in it.
Why didn't I think Lorentz factor is also a good one.
Oh.
Also the Q value. Yeah, that's good too.
When in doubt, blame the UK. Yep, they invented most of these things, and they act better than everyone now. They're like, oh, we actually use the metric system. Oh, like, yeah. Mm-hmm. Well,
Yeah.
you're the ones that British engineering units. Let's see what wacky things they did. It's not all us, you know.
Oh, okay. I've failed. Wait.
What?
Wait. Is alpha unitless?
Alpha?
Alpha is unitless. Alright, I'm going back to my original answer. Fine structure constant.
What do you mean alpha? From what?
Alpha, the fine structure constant. For electromagnetic or quantum electromagnetic interactions.
Oh, no, it is dimensionless.
So the fine. Yeah.
Oh, thank you for the
and
follow.
It's approximately 1/137.
Wow.
Yay.
I gotta follow. What? Another one?
Also, I feel disappointed that I didn't think of index of refraction. That is also unitless.
Oh, it is, huh? The index of refraction. I didn't know it was.
Apparently, Net better at fluid mechanics than you.
Okay.
All right, Net. Solve Navier-Stokes.
You know a decent bit about how water moves from soil science. Okay, yeah, you're right. Soil science. Fluid mechanics.
Fluid mechanics lab?
I'm down.
I'm scared. That scares me.
I can make the Sims in Blender.
Thank you for the follow, Terry.
Oh, Terry.
You can't have my children.
Oh, shucks.
You're not getting my children.
Kit creates PNGs. Follow me. Thank you very much. I don't have my. I guess I don't have my alerts on here. Soil. Oh, it's Terry. It just. Oh yeah, home. So you know that bit. I love that bit so much with the. It's Terry from Twitch.tv/Terrified Games. That's Terry from like just saying the whole thing verbatim by name, like a dot.
Oh, yeah, the full URL.
Yeah, it's like, oh boy, Terry, we're covering some stuff from en.wikipedia.org/wiki/soil science. Take a look here. Oh boy, that looks like some fine soil. That's.
I want to lick it.
That's the picture. 17 black. I was looking at the VOD for that too, and it's so like, he literally did
full legal name H.
Yeah, the name of your children and yeah. No, I was looking at Terry's VOD when he did the 17 black bit, and oh my gosh, he really did throw everything at it.
Oh my god.
And what's funny too is that like I actually had some crazy good luck. So I had like the best odds. I won like 6 times in a row with like really good like odds. It was like I got like a spin on the wheel. I got 2 times and I got a 5 times win. So I just walking around like I'm crazy. Why is the money going down? I was the only one that made profit.
I do remember. I think this is one that Nep struck really big on Plinko, but I wanted to try the penguin game. And
I tried it. I
was doing strangely well. Like every time I stumbled was like really early. So like I was still like if I just kept pressing the button and like doing it like pressing it 3 times and cashing out, I was still making money on average. And I think I ended up making like $500 and I was like, I think this is good. I shouldn't push my luck anymore. And then I just wandered around the rest of the night.
It was pretty cool. I stumbled into it. Like my expression on it and everything is just like I stumbled into it. I gotta find that clip. So good.
Yeah.
Hand texturing.
I was afraid to touch that other game.
The Kino one.
Like Minesweeper on it.
I did it actually. I gave it a shot and I was like, oh, is that what that is? And I still don't like it. Don't like it. But if you go to a casino, like there is a bunch of Kino, like on machines.
Oh.
Like they actually do have it. It was not fun. Yeah, I don't like it. But now that I understand how to play it.
I need to check the Steam page again, because I'm very curious why poker never showed up. I could have sworn that was on the list of games they had.
It's gotta be. It's probably one of the rooms we'll get to.
But like we made it to like day 5.
Where there's tons of floors, right?
But
it's gotta be higher. Because we got to like floor 3, right?
17 different games of choice. Oh wow. Okay, yeah, 17 different games.
Ooh, probability calculation for Kino.
I won gambling. I can't believe she won the statistics gambling though.
Now let me see what the actual odd is. Pachinko. That's not it. It's Plunko.
I mean, the payout, the maximum payout's what, like 3 standard deviations away from the center?
Yeah.
So
it's like 256 times odds or something.
What's the probability?
What?
Yeah, what's the probability you land 3 standard deviations away?
Plunko. Plinko. Spelled it wrong. I'm gonna take a look at that soils. I like how this stream just kind of turned into like we're learning some stuff up on Wikipedia and talking about it.
Yeah, this turned into a just chatting stream.
I like it. I like it. I like this bit.
But it's educational. It's fine.
Yeah, I'm telling you, Wikipedia is a valuable source. This is where I got all my theses sources.
I will say Wikipedia nowadays is a very good first intro into a given area. Like that's why when I went last night to look at that orthogonal the Wi-Fi frequency mixing thing, like it's detailed. It was detailed.
I can't find anything on it.
Like definitely don't go into like don't write a dissertation off of Wikipedia, but like if you're curious about something, it's not bad.
Yeah, no, it's totally fine. Oh, okay, here we go. The official thing is called a Galton board. Or bean machine.
Yeah, I think
So you've seen the visuals of a standard of a normal distribution with like tons of little tiny tiny things. A Gaussian board. No. Central limit theorem.
Oh, unfortunately not.
Is designed to illustrate his idea of the regression to the mean, which he calls the reversion of mediocrity. The reversion to mediocrity. What? Wait, what does this Galton dude do? Hold on.
Weird way to phrase that.
It was another polymath.
Because the central limit theorem is just for large n, for large sample sizes, a random distribution becomes normal.
Oh boy, this guy. Okay, interesting. So he was. Let me just read you the article. So it says Sir Francis Galton was an English polymath and the originator of eugenics during the Victorian era. His ideas later became the basis of behavioral genetics. Okay. Interesting. Hold on, what does that article talk about? I forget, is eugenics considered good or bad? Socially.
That's bad.
Okay.
Eugenics is bad.
Ah, okay, just making sure. Eugenics in Mexico. Okay, let me get out of this. So,
stats are eugenics. Oh yeah, sure, Tyler. I'd like to see you get away with telling Mylan that.
Well, hey, you know what? He had a pretty good explanation for it. I'll tell him that. Galton board, reversion to mediocrity. It made part of his eugenist ideology. Oh that's so okay. Good job, Nep. You beat eugenics.
All fairness, a lot of scientists did have their clawed skeletons in closets.
Oh no, it's actually really interesting. I like learning about all the sorts of crazy stuff that like people believe in. And you know what? That's still a thing now, right? All sorts of like wacky scientists have all these really like radical ideas. And it's like that's crazy.
Did you know that Feynman had a hobby when he was at Los Alamos of guessing people's combinations to like their lockers and cracking, like just getting into everyone's lockers.
Why?
Or like their drawer. Yeah. I don't know, but he was really good at it apparently.
That's weird. That's creepy.
Yeah.
That's all these wacky scientists, man. Let me see more about this Galton board because that's the official name for the Plinko, I suppose. Let's see, beats are dropped, blah blah blah. Underlying a Pascal's triangle, yeah, basically.
Oh yeah, that.
And it's demonstrates the binomial coefficients. So.
Yeah, Fibonacci.
Fibonacci. I want to do a stream one day talking about Fibonacci and just him specifically. Apparently, he did a lot, and one of the things he did was change from the Roman numeral system for math and numbers to the what was it? Arabic numerals, Arabic numbers. Yeah.
Oh, I think I vaguely remember that from my history of math class.
Oh yeah.
Because I also had to take that for math major. Yeah.
I didn't.
I will be honest. I don't remember much of that class.
It's
All
okay.
I remember is something fairly juvenile about sine.
Okay.
What we call sine is because of a mistranslation from the Hindu texts, because the trigonometry was originally developed by the Indian astronomers to try and track star stuff. But it was translated into Arabic when the
Arabs,
those people, the Arabs translated it for their House of Wisdom, and then when the Europeans managed to salvage some of those texts a lot later, they had to translate that into Roman or to Latin, and then
Let me look that up. That sounds interesting. Sine, cosine. Interesting. Background. Entomology. It's from Sanskrit. Referred to as a bowstring.
Oh.
And then transliterated from Arabic as that, and since Arabic was written with short vowels, was written without short vowels, jib became interpreted as jaib, which means bosom or pocket or fold. In regard to what? And then later,
so yeah, we have a function called
sinus, which means bay or fold, or hanging over like a toga over the breast of a woman. Hold on, wait. Which means the bay or fold, more specifically the hanging fold of a toga over the breast. Okay.
We have a function called boob of x.
That's basically it, isn't it?
And the co-boob.
The co-boob. The second one. Yep.
Yeah.
I'm gonna explode. I'm gonna guess Tyler. Ducky has exploded. I like that command. It's so good.
I should make a random one.
What didn't you do, Tyler? Okay, so we're learning now that everyone, mathematicians and other characters have their skeletons in the closet. Let's go find someone who's racist. I want to find a racist.
A racist?
Yeah. There's I told Fasan this. If I ever get into like a role-playing game, I want to be a racist mathematician.
Like in D&D?
Yeah.
Isn't that just an elf? That's just an elf wizard.
Is that right? Oh, that would be it then.
I mean, yeah, elves are canonically racist in D&D.
But it's gotta be like in the job description. It's gotta be like racist, racist.
Oh.
Yeah.
Well, I mean, you can build into the backstory that in order to get your wizard position and graduate from elvish wizard schools, you had to be a certain amount of racist.
I passed the racist exam. It's How do you get good at it?
If we're talking about D&D, I once absolutely destroyed my DM's one shot by accidentally just persuading the heck out of like a pirate crew.
Oh, really?
Yeah. We were supposed to have this giant fight, but when we were like when they stopped us and like confronted us, I was literally like, they're like, what are you guys doing here? I was like, I'm the captain. I was like, okay, are you really gonna try and argue that? I was like, yes, I'm the captain.
I'm the captain.
Why are you trying to fight us?
You had a roll. Did you roll well?
I rolled a nat 20 with disadvantage.
Really? No way, dude.
Yeah.
That's crazy.
So and the DM acknowledged that. He was like, I can't believe that happened. I was like, yeah. So he let us get on the boat and just sail away.
That's ridiculous.
I don't know a racist scientist, but I know.
I'm finding out there's a lot. There's a whole section.
There are a lot of womanizers, and there was a pedophile.
Oh, yeah. There's a lot of that. No, I want a racist. Yeah. I don't want like crazier stuff. Well, I suppose. Yeah, that comes with the territory, huh? Like, what? I have to start narrowing it down. I want particularly a racist biologist, but also, let's say British. It's probably a lot. I'm not gonna lie. It's like a bingo, like a cursed bingo card. Is that scan well?
Why is this scientist an asshole?
Yeah, let's find out. Oh, because his
you got A, B, C, or D.
Oh, that's a good one. Yeah. That's a good one.
In fact, you're a DM's nightmare. How dare you?
I'm looking up articles of our names right now. So Nepenthes.
I mean, the DM, in my defense, the DM could have just said no and made us fight.
Miranda.
In that same one shot, one of my friends made someone pee their pants.
Huh?
Or it made it look like someone peed their pants. And yeah.
That's how? Do you like
She
in game? Or like IRL?
Yeah, like if you cast no, although that would be funny. No, like so she cast Prestidigitation, which is a cantrip that allows you to conjure like the either an image or a smell or like a sound. It's like it's a weaker version of like minor illusion.
Oh.
And so she made it look like someone's pants were wet, and then she made everyone else in the room make fun of them.
It's like, oh yeah.
And then we snuck away.
I won't take you seriously because it looks like you peed yourself. Yeah, Terry. You really just...
mean, yeah.
Consider your pants peed.
As a DM, I know that.
Pretty good.
Not that bad of a player.
That's still funny. Why wouldn't you do that? Look, I'm checking out the article for Nepenthes. This is like a biography.
Oh, is Nep on there?
Yep, Nepopotamus right here. Genus of carnivorous plants. Tropical pitcher plants or monkey cups. Should I call her monkey cup? Is that okay, monkey cup? I will refer to you as that. Why? Why is it called that? Well, there's different things here. Does Aleph know about the Nepenthes that mice use to poop in? Wait a second. There's a toilet Nepenthes? And no way.
Yeah, I vaguely remember that.
There is? You got grass in Animal Crossing. It referred to it. We don't make these jokes. Yeah. Interesting. And the entomology from Homer's Odyssey. Just a potion is given to Helen by an Egyptian queen. Nepenthes.
Oh yeah.
Literally means without grief. And in Greek mythology is a drug that quells all sorrows and forgetfulness. I call that alcohol.
Yeah, because it's if I remember correctly, you can make like a light aphrodisiac out of it or something. I know that. So I did find out in random googling that the Nepenthes plant can be used to. It can be used as a what's it called? A pink fluid when you have an upset stomach.
Oh.
Why am I blanking on the name?
A remedy? No. Okay. We've upset Nep. We've upset Nep.
Oh. Pepto-Bismol. Yes.
Okay. Nep, come back. We're sorry. I'll move on. Pepto-Bismol. So like when your tummy hurts, you can.
Yeah. So it has those properties. I actually made. I have no idea where it's saved. I made Nepto-Bismol.
Nepto. Come back.
It's not in. I have no idea where I saved the file. Alright.
I get it. Let's not make fun of pitcher plants anymore. Tyler brought it up. It's his fault. I do like it though. I like the plan. Question for you.
Yeah.
Tyler blew up.
Yeah.
Good job. Okay. Question
It's
for you.
bound to happen eventually.
Yes. Are you familiar with a Poisson distribution? I remember this bit. I was talking to Poisson about this, and that's basically what gambling is, right?
Yes.
So there's actually a very well edited video Poisson made. It's got Max War vibes. It's crazy hilarious. If you've seen it, it's so good.
It shows up in StatMech too. If you take binomial distribution, I think, and you take like a large limit of it, it turns into a Poisson distribution.
Interesting.
Yeah, probability. Wait, so discrete probability of a given number occurring within a fixed interval of time or space, assuming these events occur independently. Yeah. Yes.
So, are you familiar with that one dream drama from Minecraft about him getting crazy high odds on ender pearls and stuff?
No.
Okay. So I suppose instead, we'll talk about, you know that you
Are
can't...
drop rates Poisson? Are drop rates? Do drop rates count as a... Oh, I guess they do, yeah.
Yeah. So anything that has to do with a roll or an odd, but you rolling for it, you know, it's literally like the math equivalent of like how many days since an accident, you know, accident free since 55 days, 56 days, 57 days.
Yeah.
Yeah, so it's like that, but like you actually know your odds of it, if that makes sense. Which is pretty interesting because you can do a lot with that. So yeah, game odds and stuff. You know, at some point when stuff should be happening. So when they don't match that statistic, there's something sketchy going on, right? So like I expect to win in about 5 games, right? Like that.
Spoiler: he cheat.
Yeah, he ended up cheating. The dude. Want to hear something crazy? So during that drama, he actually had to hire. He hired like an astrophysicist to do the statistics to demonstrate that he's not a loser, that he's not cheating. He did lots of crazy, stupid stuff just to prove. But like, my question is, why hire an astrophysicist for a statistics question? You know?
They do a bunch of statistics.
Nonsense. You'd have to call for a statistician to do statistics. It's kind of like in the name, right? you see
yeah, but like...
See my point?
I mean, I feel it's the same thing as like, you can get a physicist to teach calculus, right? They took the same calc class.
I know, I'm just being...
that a math major would take.
Very facetious.
Yeah.
PV, you have to do statistics.
Oh, statisticians are superfluous.
Yeah, they're extraneous. Stats isn't real. Yeah, astrophysics, smart, work with numbers, smart. Giving the lack of better phrasing, it sounded cooler. Yep. It's ridiculous. Stats, no. I love that bit. Oh, Gauss has died. Are you there?
Alright, I'm back. That was weird.
You disappeared on my end. Ouch. Oh, thanks. Let's see. How you doing on time right now? What's the vibe like right now?
I mean, I will admit I am kind of running out of steam.
Yep. But we're not playing any games. Joke.
I mean, VTube Studio is on Steam.
Actually, I noticed how many hours I have in that already compared to something like Blender, and I'm like actually surprised.
Oh yeah.
I'm actually really surprised already. I thought I'd work on that a lot.
Actually, let me see how many hours do I have on VTube Studio? I have that is a lot more than I thought.
Right? It's
I have a full 3 days.
3 full days. My number's gone up since then.
And 2 hours.
But let me see mine. What do you say that we wrap up pretty soon and then we can go get some, I don't know, dinner or something if you haven't eaten already. I'm gonna get something. This is here.
Yeah.
249 hours.
I mean, I should probably go to bed soon.
Nah, you don't have a bedtime. The history of time.
I mean, I technically don't need to go to sleep. It's not like I have work in the morning.
Oh yeah. I actually don't work tomorrow. Again, this entire week is great because I get to just do nothing now. But I like this. This was like a vibe. Like we're just talking about something with a general theme, and we kind of just kept exploring around. It's still pretty fun. Let's see. We're back at the computer lab, just sharing each other funny memes. Oh, I read this book, the Griffiths Electrodynamics book.
Yeah, that's what we used for intermediating them. Oh. Actually, that's what I've been doing my ENM series out of.
Yeah, I like this one. This one is pretty good. Maybe we could do a discussion about like books and stuff. What books did you actually use?
Yeah.
I have a few that I still have from physics, but a lot of them I ended up just, because it was physics, I ended up just having like a totally legal copy in PDF form.
I mean, I do too.
Yeah.
I have bought, over the course of my degrees, I have bought 1, 2, 4 physics textbooks in total. No, 5 physics textbooks.
Really?
Yeah. One of them was because I had to, because the professor used their own book.
Interesting. They could your professors.
But yeah, Griffith, like for physics majors, Griffiths is one that I do recommend you buy, because especially if like you want to go to grad school for physics, it's just really good for ENM.
Like it's that good.
It's that good for like the intermediate level. So like it covers a good deal of the concepts. And a lot of times if you have like prelims or quals, you'll actually want to brush up on the undergrad stuff because the graduate level stuff is more recent.
Right.
So
okay. I'll give that a shot then, because this is one of the few books I actually really did like, and I'm forgetting a lot now. Actually,
yeah,
it's been a minute.
No, I also really liked his explanations in the book. That, and I liked my Quantum 1 textbook. That was good. But yeah.
I'm just calling Terry out right now. Let's see. Yeah, we can probably finish it up right now. Let's see then. Suppose we can raid somebody. If you're down,
yeah.
Finish up right now.
Yeah. Let me pull up my Twitch.
Twitch.tv/. There's a few people I could recommend, or we could always just find a new person and assimilate them and make them our friend.
Yeah. Yeah. I usually try and see if there's one that looks interesting to raid.
Software dev.
I don't know. This is, yeah. The issue with a lot of these, like for like same category, is like it's just a bunch of random like, I don't know, like live cam stuff.
You want to rate a VTuber?
Yeah. Can I filter by VTuber? Oh, filter by tag. Duh. Okay.
What tag you're going? Oh yeah, V2. Yeah, there's a few. Final Fantasy X. What?
No, there was one that was very interesting.
Okay. You'll have to tell me what that was in a sec then. If you see something.
There's someone playing Subnautica 2.
I think I see that one too.
𝖘𝖔𝖈𝖎𝖆𝖕𝖎𝖙𝖘.
𝖘𝖔𝖈𝖎𝖊𝖉𝖎𝖙𝖘. Okay. Let me look that up. If I can spell right. Send it to me. I found another Subnautica player as well, also.
Oh.
When in doubt, let it ride. Exactly.
There's also someone playing Genshin.
I see someone, also a Subnautica 2 player. 𝖘𝖔𝖈𝖎𝖊𝖉𝖎𝖙𝖘.
How do you spell that?
Spelt like... Manually type it out. Cozy streamer. Let me... Yeah.
Oh yeah, or if chat has any... Oh. Oh, there we go.
She's got 3 viewers. I feel like we can give some love. There's a bunch of nerds.
Alright.
Yeah?
Alright.
Give that a shot?
Yep. This is good.
Cool.
Yep.
Alright. Then let's do that. Have a good night.
Let me
do your outro. What's the next time we're gonna see you?
Yeah. I am actually going to go on a short hiatus because I'm going home for a couple weeks. I will be back. I will not stream again until June 17th, but I'm not, don't hold me to that, because the reason I haven't been as busy this past month is because my summer is supposed to get extremely busy once I'm back from visiting home. So we will see.
Yeah, no worries then. Let me tell you then, because I will be preoccupied basically the entire summer, because of like job stuff and living arrangements for that. So I will be away. It's a temp thing. So I probably won't actually be able to
still
stream.
be on Discord.
Yeah, so I'll have to be engaged a lot more offline. That makes sense. Not on stream. So this might be our last collab for a while. Just hanging out. So we'll still obviously hang out and stuff, but just letting you know. And because I liked how today went. It's pretty chill vibe, right? So
yeah,
really cool, really cool. So I'll we'll do our best. The next one is gonna be really fun. I hope we'll plan something really good. Because my hiatus is gonna take a lot longer. I won't be back until August. So.
Ooh, yeah.
It's like completely out of the way.
Right.
So I'll try to bug you in your chat and stuff.
Yeah. Oh, I guess I'll have an idea when I get back from break how busy the next couple of months are gonna be.
For sure.
For once I'm hoping it's busy because I'd like to graduate sometime soon.
You will? Oh yeah.
Yeah, and I'd very much Because I'd also very much like to have a celebration when I get my first author paper. I think that would be fun to celebrate not on campus, on stream.
Right. That'd be cool. Let us know. That'd be totally
is graduating. I wish I still have like 2 more years.
That's a good ways away. I'm hoping to catch up with that as well, and also be on the graduation train. Man.
Stop stream. Oh, stop streaming. Yeah, I'm only streaming until I get my doctorate. Then I'm done. I'm done.
That's how that works.
Yeah.
Understandable.
I'll be a real boy then. I don't need this.
Right.
All right.
Let's go ahead and.
Yeah. Let me start the. Yeah. Let's start the raid.
Yep.
Thank you guys for joining us. We will see you when we see you.
Yes, that's right. Have a good night, and bye-bye. 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 Bye-bye.